All right, so we spoke about yesterday. We spoke about the caloric theory, and we said that the caloric theory is a theory that somehow considers heat to be a fluid, right, flowing from a hot object to a colder object, right? And but this is so because they thought that as the hotter object and the cooler object come in contact, the hotter objects would get colder and the cooler object will get hotter, right? But we see that this is not correct because of the kinetic theory of matter and motion, right? It says that all atoms, if I ask you to state the kinetic theory, you should say that all atoms have some form of motion and exhibit perfectly elastic, right, collisions. So that means that all atoms have kinetic energy. All right. Um, Perfectly inelastic collisions mean that no friction is lost, no energy is lost, right? Remember from the law of conservation of momentum. What was that again? What was the law of conservation of momentum?
Sorry, yes.
Yes. What is the law of conservation of momentum? Remember we spoke about that, I think last week. All right. So I
Sir,
know
I remember. Tell me, sir.
I don't. I seems as if we don't remember or we're not reading over our notes, right?
Some more energy not being able to be created or destroyed. So it is stored. Well, an energy that is left over is stored.
No, that's not it. That's the law of conservation of energy, right? We're talking about momentum. It says that the
Oh,
initial momentum, remember this?
initial velocity.
Right, one second. Right, initial momentum equals to what? What is this equal to? Initial momentum equal to what? Final momentum.
Kinetic
Kilograms, sir. Kilograms.
No.
MS.
All right, let me just skip back to that quickly.
So equal to M1 V1. That
Right.
person. That
Yes, that particular slide.
oh
Yeah.
M1 V1 plus M2 V2.
Equal to the momentum after the collision, right? Well, let me
Yes.
just bring it up for everyone. Lectures. So remember this law of conservation of momentum. Remember we went through this.
Yes, sir.
Yeah. So when these atoms collide with each other, they exhibit perfect elastic collisions, right? So you'll find that the momentum before the collision will equal the momentum after the collision, so therefore no heat is lost. Right, so that's what we assume when we're talking about the kinetic energy theory of motion. Right, so we have elastic collisions. As we said, these will separate after the collision. So they won't stick together like inelastic collision. All right, they will separate after the collision. Okay, just doing a quick recap of what we did yesterday. All right, so from the color theory, if we actually believed the color theory that it was true, then when an object gets hotter, it would gain caloric, right? It would gain caloric. And remember, we said that they consider heat or caloric as a fluid. So therefore, additional substances would be the on the object, right? But there's no evidence to prove that an object gets heavier when when it actually gets hotter, right? There's no evidence of that. So therefore, this is a no-no. This makes no sense, right? But the kinetic energy theory, right? We can prove the kinetic theory by Brownian motion. And we said this was again yesterday.
So yeah, you're saying.
You not hear me? Remember we spoke about the Brownian motion? All right. I'll repeat it one more time. So you'll find that large molecules, if we observe large molecules, they will have a random motion in the air. So that means that there are small particles that are actually constantly colliding with these larger particles. So if there were no small particles, then the larger molecules, they would act or they will move in a uniform way, right?
You do have to ask some, so you can ask them run at the gate, because I don't know.
Right, so if there were no smaller particles, you'd find that the large particles would move in a uniform way. But because you have smaller particles, then you'll see that they have random motion. Therefore, all molecules will have some form of motion and therefore kinetic energy. And we went on, this is the heat capacity, and one of our classmates said that heat capacity is the amount of heat energy that is required to raise its temperature by 1 Kelvin, right? And what is the difference between heat capacity and specific heat capacity again?
The mass, sir, as by mass.
Right, so specific heat capacity, on the other hand, is the amount of heat energy that is required to raise 1 kilogram by 1 Kelvin. It's essentially the same, but in this case, we are taking 1 kilogram out of that object to see how it will react rather than, right, the a large amount of the object or a large mass of the object. And we also did some questions, right? And I hope we got the time to go through these from yesterday. All right, so for today, we'll take a break on heat capacity and we will look back through some of the labs. I am currently at school, I'm collecting the lab books today, and I will take them and mark them, right? I'll take the lab books today and I'll mark them. But we didn't, question?
Yeah, man, so I don't have a lab book yet. I take official one.
Yeah, so you have time. By the time I am finished marking, right, it should be no more than a week or so.
Sir, can you
Yes.
look at this? screen, the kinetic theory screen, please. I'm taking notes right now.
Again?
And you put about the kinetic theory screen, the screens. That's right.
You're writing it down?
Yeah.
Yeah, the notes are in Google Classroom, so you don't really need to
No.
write. But I'll
Like
put
when
it
you
up.
share screen now,
Sir,
sir.
sir,
Question?
sir. So did you get my lab book, sir, and the SBA?
I haven't collected them as yet. I'm waiting on Mr. Pierre to come to school. Alright, he has them now. This is the screen you're talking, Terry.
So did Miss Young get the SBA?
What again?
Miss Young, did she get the SBA?
Miss Young?
Yes.
I'm not sure. Who is that? Who's this one?
Remember me call sir and ask if you ever go to school the next day and you say yes. So leave it. Yes, we.
And leave it with, I told to leave that security guard.
Yeah, with the lab book, sir.
Alright. So I'll check on it.
Right, sir.
I just reached school and as I came to school I just go straight to class. So I'll check on it afterwards. Tyrese, are you finished?
Right, sir.
Almost.
Alright.
Oh shit, man. Sorry. I realized.
Right, sir.
Alright. Alright, so based on the feedback after the submission of labs, right, I saw where there were some misconceptions as it relates to some of the lab. So I will ask you now. Right, let me plug in my charger for this thing, guys. All right, we're going to go back to the labs again, and we're going to identify what is needed for the labs, right? I believe this is very important moving forward because some of the labs require plotting a graph, and that's why it was important for you to do the draft lab. So after you get the draft lab, in the meantime, while I'm marking, for those who haven't plotted graphs, please, this is the time you can use to plot your graphs to fix up your discussion, right? If you haven't given me the best of your abilities, that's up to you. If you feel like you have done that, that's also up to you.
Sure.
Question, yeah.
Yeah. You got graphs in class, sir.
Repeat?
You plot graphs doing the lab.
I'm not here.
Did we plot graph during the lab? During
You plotted graph during the lab?
No, I'm asking, did we?
Right, and some of the methods told you to plot a graph, right? So the reality is we wouldn't get the time to sit down in the labs and plot the graph. The reality also is that, right, it's not normal for you to plot the graph at school. Usually you take home the results and you plot your own graph, right? If you want, you could plot it at school, but the reality is that we didn't have enough time at school to actually plot the graph for each labs. The marker is saying something?
The lab 8.
Lab date?
8.
Yeah.
Last one, I need to do over.
Last set of labs?
No, that's the last one I went to with the glass.
Snell's law? Yeah. So I gave you the results. We will talk about it. I sent you a video. Did you get to watch that video?
No, sir.
No, you didn't get to watch the video. So I'm putting out effort.
Moments, sir.
Go again?
Moments.
About what?
moments, the two video they made upload.
Yeah, I uploaded one with Moments and I uploaded one with Snuzzler. Did you watch that one?
Yes, sir.
All right, so I'm trying to put in an effort to do my best. The time is limited and we're trying to complete as much as we can. So for the first one, right, we won't waste any more time here. The first one, you were supposed to plot a graph of extension versus load. So which one would you have on the y-axis? Extension or load?
Extension.
Right, so extension would be on the y-axis and you have your load on the x-axis. If you didn't know that, write that down right now. Right now, get a piece of paper, put it in your phone or something, write it down. Because if we look in, right, if you look here, we will have to state the relationship between force added and extension, and the only way that we can do that is through the graph. So if we somehow get a graph of, let me try to get a blank paper. Yeah, let me try and get a blank sheet or something that I can write on. Alright, just annotate. Yeah, so if we somehow get our results, it's expected that we draw a graph in order to be able to determine the relationship between um between between extension and load. Right? Let me draw. So we would have a graph here. We have our extension, right? Which is this. We can say let it be x. And we have our load, right? We can, our load is what exactly?
Mass, sir.
No.
Mass.
No, the force. Wait.
Right.
Wait.
Right. So that would be weight, right? And that is
The
in
y on
newtons.
the x-axis, sir.
Go again?
On the x-axis.
Yeah. So weight would be on the x-axis. Are you seeing this, the annotation?
Yes, sir.
All right. So and then you will get a straight line. So from this graph, what can you say about this? What is the relationship? Inversely proportional, directly proportional, right? Which one of them?
Directly.
Right. So it'll be directly proportional. Let me get this. What is this now? Mouse. And so this will be directly proportional. As we said, we didn't have time to go through this. All right, directly proportional. So as the weight increase, what happened to the extension?
It's stretch.
It also
increase.
All right, it also increase. All right, so let's get rid of this. Next one, next lab. Is there any misconceptions in this? Anything in the questions that you didn't understand?
Plotting the graphs.
What I mean by directly proportional?
Yeah, the Hooke's law from the one. Directly proportional.
All right, so somebody, we need to go back to our notes, right? We need to go back to our notes on Hooke's law, right? You can check Google Classroom for your notes. Everything is there.
Applied, sir.
Go again?
Oh, never mind. Graph easy apple. I mean, the vertices are out to plot the extension, sir. Or like which number we start? 0, then 0, 5. We can try the same number then.
Yes. All right. So you start at, just an example, right? Let me get this out of the way. Example, as you said, we have weight down here, newtons, and we have extension. Now you start at 0. Why? Because remember we had our spring here, and this is the zero mark with no weight on it, right? So
That's
as we begin to add weight, you would have say an extension of probably 5 centimeters and 10 centimeters and 20 centimeters. So you would have 5, 10, 15, 20, 25, right? Understand?
yes, sir.
That would be that would be the weight, sorry. And then if you have an
What are the
extension of say 10, just an example, 10, then 20, then 30. So
what
say your
answer?
point was 5. Question?
Eh,
How
so wait there. Well, why now with table we have on the something right here, sir?
Yeah.
No, that's a graph. You should have a graph paper. I just said that
Yes,
you
sir.
will have a
That
graph
me say
paper.
that me mean.
so may I
Yeah,
say
the
if I
values that we're using, that would be on your table, right? I'm just giving an example.
don't have a draft? Oh, all right.
All right, so if your point was 5 and 10, if your point was 5 and 10, you would match up 5 and 10. All right, 5 and 10, and if your other point was here, the other point was here,
Sir,
right? And then you would finally draw a question.
you have to go to over and make mention of the graph.
I didn't hear.
I didn't mention of the graph in my this or in go over the lab, sir.
No, remember, this is a draft. So
Yeah,
you
but
will
we
have
said we should mention of the graph.
in a discussion.
Yes, sir.
Yeah, so you say a relationship in a discussion, right? So if you haven't done so in the draft, then just ensure when you're writing up in your official book, you mention the relationship if you
Sir,
haven't done
you have
so.
to come to you and look if it's correct first.
Go again?
Confirm it's correct first, sir. You do it in your meaning we can't put the official bit
You haven't
and
gotten
we must
answered?
say correct. Have it, sir.
No,
You
you will
must
wait
put the
until
results of the
I
graph.
return the draft books. When I return the draft books, you come back at the security gate and you collect them. That's the time that you can make the relevant changes.
What is not correct?
No problem. If it's
We
not
still have
correct,
get we still got change, yeah, correct.
it's not the final. You're not going to lose the marks here. I just want to see where we were.
Oh, I understand. We understand it and thing.
Yeah, I wanted to see if we actually understand the labs. I don't. If in my time you just had to submit the lab, just submit the final lab. No draft or not. Not the teacher don't want to see in the draft, but we're making it clear that we want to see how is it, how if you really understand the lab, and then we give you back the book, right? We explain it, and then you'll finally submit it just to clear up any misconceptions.
Sure, so may I
Okay,
want to
sir.
know how much marks the labs in here?
So each lab is about 10. You have to look on the mark scheme, and you have to look on which part of the lab is very important. So procedure, you have 3 marks, right? You have table, neat headings with units. So you have to look on these marks and say, okay, I have to ensure that my table is neat, my headings, right, are there with units, the proper units, changes to kilogram, right? Have your newtons here and so forth. And you want to state the relationship between force and added extension. Force added and extension, right? This is 4 marks. So you want to make sure that this is done properly. All right? All right, let's move on to the next lab. I believe we're finished here. So, all right, let's just say use the graph to predict what extension will be if a force of 0.775 newtons is added. All right, so I believe the scale is too big here. Yeah, I believe the scale is too big. So say we had 0,
Sir.
0.1, right?
Sir.
0.5, question?
Yes, sir. 0.7 Newton as in the extension, sir.
As in the weight, newtons,
Oh,
force. So it come to 0.75 here, and you would draw a line. You would draw a line up to the line, up to the actual point on the graph, and then you come across here to see what the extension would be. So the extension here would be approximately 55. So your answer would be 55 centimeters or 55, whatever you put it in, could be centimeters or meters, right? 55 centimeters extension at 0.75 newtons.
Sir, what for the funny scale weight and stretch length?
Extension on the y-axis,
Yeah.
weight or load on the x-axis. I will not say it again. I will not say it again.
Excuse me, sir.
Question.
Should we start the weight at 0.1?
Yeah, it depends on your scale. It depends on your scale, and you are free
But
to
one of
set
the questions is 0.75.
Where does the value stop?
7.
It stop at 7? All right,
Yes,
so change this to 0.65 then.
0.65.
Yeah, at the time I was writing, I didn't know that it could go beyond. I didn't know that it could go beyond 7. So change this to 0.65.
As I was saying, sir.
Yeah. Yeah, so at the time I was the one that drafted this. I came up with this, right? So I came up with all these questions, which would help you in writing a discussion. I did not know, I had no experience with the spring. I didn't know how far it could stretch. So this changes to 0.65. Any more questions?
Yes, sir.
Sir.
All right, I hear Mr. Noble and I hear Dean. DeMarco, sorry. All right, so Mr. Noble, go first. Well, we have less than a minute.
All right, sir. About the thing where sir. Whenever they are here, like India, is the only problem.
Okay, so
all right, sir. When we did the discussion, I never really do it like from 1 to 8. I do it from 8 go straight up.
it doesn't matter which order. It doesn't matter which order. All right. Yeah, man, Mr. Noble. Are you hearing me now?
Yes, sir.
All right, so we'll stop because we have less than a minute, and then come back. All right.
All right, sir.
All right. So we'll stop here and then come back. So I'll end the call. Please join as soon as possible so we can cover everything. Mr. Noble, come first. I will answer your question. All right. Yeah,
Yes, sir.